So when we study the Earth's history, we can actually use the rock record, which is the rocks that are there, and that'll allow us to paint a picture of what has happened in the past. In order to do that, we have to have a couple agreements or a couple ideas that we all hold to be true, and that allows us to use these ideas and carry them over so we can understand what the rock record is trying to tell us. The first of these is that the rock record is going to provide evidence of geological events and life forms. So this allows us to say that the rock record is actually going to tell us what's been going on, and that makes it kind of useful. The second is a process that was presented to us by James Hutton of uniformitarianism. And what it basically says is that the processes observed on Earth today also acted in the past. So there's not some new processes that were happening now or some that no longer happened that happened in the past. The same things that shape the Earth now are the same ones that shaped the Earth then. And then finally, that the Earth is very old and it's changed over geologic time. So we've had time for all of these things to happen. So using these three ideas allow us to study Earth's history in the rock record. Now, when we talk about dating, there's several different kinds. The first one is going to be relative dating. And relative dating doesn't give us exact dates. It just kind of lets us say that this layer is older than that layer, or this layer is younger than these two layers. It allows us to age things relative to the other layers that are around it. Now, for us to be able to do that, we have three different laws that we use. The first one is the law of superposition. And the law of superposition can best be described in this type of example. What it's saying is that if we have multiple layers of rock that are undisturbed, the younger ones are going to be on top of the older ones. So let me show you what that means. Let's say you go to school on Monday, you get home, your clothes smell like school, so you take them off and you throw them in the corner. So you have Monday's clothes here in the corner. Then Tuesday comes and you do the same thing and you take Tuesday's clothes off and you throw them in the corner over here as well. And you do the same for Wednesday. And we throw those in the corner. Now what we know is that we have Monday on the bottom, we have Tuesday above that, and then we're going to have Wednesday's clothes on the top. So the oldest layer is going to be Monday, and that's going to be on the bottom, and the newest layer will be Wednesday, and that's on the top. And that's what the law of superposition says. And it kind of makes sense. We can't lay down a rock layer on top of nothing. It has to happen on one that's already been there before. The second one that helps us is what we call this principle of original horizontality. What that means is that we're talking about sedimentary rocks here, and those are the layers that we're going to be looking at. And what we notice is that sedimentary layers are going to want to lay down in a horizontal manner. So originally, that's what they're talking about. It's all these layers were going to be this way, and they'll stay that way unless they're acted on by a force. So if we see a bunch of layers that are looking this way, we can assume that the oldest are at the bottom and the youngest are at the top. And then our third and final principle is this principle of cross-cutting relationships. And that one makes a lot of sense if we look at the picture. And what we're basically saying is if we look at this fault here, we have fault A. Notice that fault A is going to break through these layers, but not this one here. So that means that for it to break through the layers had to be there before it. So that'll allow us to say that this conglomerate layer is going to be younger than this sandstone layer because the fault doesn't go through it. And the same can be true for not only faults, but also if we have igneous intrusions like this dike coming through here or a sill forming here. Now, when we use all three of these principles or these laws, it allows us to age our layers based on their relative age to each other. So we can't get an accurate age. We can't say that this layer was this many years ago, but we can say it's older or it happened before this layer. And that gives us the benefit of just kind of relatively aging things. Now we have two other clues that allow us to read the rock record. One of them is inclusions, and inclusions we can see down here, this inclusions of igneous rock. What we're looking at is these bits and pieces. So if we have bits and pieces of something inside, then we know that this layer had to be here first so we could break these other pieces off that could then be incorporated into the layers above it. So we know that below is going to be older again. Now, the other one we talk about is you'll hear these unconformities. And unconformities are where we have gaps. So if we see that we had this yellow layer here and then a blue layer here and then this kind of browny layer here, notice how they've eroded away. So as they erode away and we have this missing part of the rock layer, that's what we'll call an unconformity. And both of those kind of help us read the rock record. Now here we have a cross section of the Grand Canyon, and you can see where we have some of these unconformities. And what that means is we're coming up here and we're going to have these, like this angular unconformity, these gaps in the rock record. These are going to be breaks where it doesn't necessarily match up with the rock layers that are there. And that kind of helps us gauge and estimate ages and other geological events. Like if we had sedimentary rock, but then suddenly it dried out, we're not going to have more sedimentary rock forming until we get that water come back in and allows that sediment to settle. Now, if we look at rocks in different areas, we can have this correlation of rock layers, and that kind of paints a better picture for us. If we have the Grand Canyon here, heading up the Kaibab Plateau, we get to Zion National Park. And what we notice here is that we have this Kaibab limestone layer, and we can see that here as well. And then we have this Monkopi Formation that's above it. We'll see that there. So what we can do is we can start to match these. We can correlate these, and we can then say that these formations would actually be up here, but they've either eroded away or they were no longer an area where sedimentary rocks could be laid down in the Grand Canyon. Okay, so that's a quick introduction to the rock record. As always, the lessons will explain it a little bit better for you. Good luck on your quizzes, and we'll see you in the next video. Okay, so here you can see a list of the 6 major types of fossils. The first one are these petrified fossils, and this is where we have mineral-rich water soak into the cracks and pores, and these minerals will precipitate out and form a fossil. And a really good example of this would be like petrified wood, where we have a wood sample where we have water flowing through it, and as the water flows through it, the water might, but it'll leave minerals behind, so it kind of turns to stone, and that's what that petrified means. The next type is a mold. And a mold is if we have a hard part, like a bone or a shell, that falls into sediment, then what will happen is that rock will form, the shell will dissolve away, and you're left with a hole in that sediment, in that rock, and that's what a mold is. Sometimes when we have a mold, we'll have minerals kind of come through and they fill that mold, and then we'll have a different type of fossil called a cast. Now, if we have something that was living and we apply a lot of pressure, that pressure can squeeze out everything else and it can leave behind this carbon film, and that's what we call a carbon film. And normally these are going to be plants, and it's just going to be like the image of the plant pressed onto another rock or something of that nature. We can have preserved remains, and that's if we have a frozen organism like a mammoth that's been trapped in the ice, or we can have an insect that's trapped in amber like we saw in Jurassic Park. So this is where we have one that's trapped in something else and it gets preserved that way. And then finally we have trace fossils. And trace fossils are indirect evidence. So it's a trace the animal left behind. So things like a burrow for a worm or something that kind of went its way through the sediment and left that hole, that would be a trace fossil. The same could be said for footprints, and then for coprolites, which is going to be fossilized dung. And these can give us clues as to how the animals lived, but it doesn't really tell us about the animal other than just providing a little bit of like trace evidence, hence they're called trace fossils. Now, fossils provide good evidence for the history of life. And there's 2 different things in here that we have to talk about that allow us to use this. The first is the theory of evolution, and the theory of evolution says that organisms change over time. So if they change over time, what fossils do is they give us a clue as to how they've changed or what they've evolved from. The other thing is fossil succession, and that means that we have different fossil organisms at different periods of time, and they don't live across all of them. So we can see how we have a fossil that's changed over time, and that'll show us the evolution, but that's because we have fossil succession. Okay, because we can use fossils and these fossils have this successional pattern, we can use them to help us age rocks in different locations or at different layers in the same location. By looking at this Unit A rocks, what we're able to see is certain animals and certain plants were there, and we see fossil remains of them. We can do the same at a different layer, and what it gives us is the ability to put a relative age on them. If we see a trilobite fossil here, we know that they went extinct, so we can kind of get a rough age of when rock B was. And we could do the same with C when we're seeing the advent of like this maple leaf. We know when the maple tree started to show around, and it gives us a relative age as well. Okay, so that's it for our video. As always, good luck on the lessons and the quizzes, and we'll see you in the next video. Okay, so to get started, we should talk a little bit about nuclear decay. In nuclear decay, what we're talking about is a radioactive atom, and that radioactive atom is going to have an unstable nucleus. So that nucleus is going to undergo nuclear decay until it can form a stable nucleus, and oftentimes that'll be a different element. So in our example here, we have iodine, and iodine is going to be radioactive, and it's going to decay down into xenon. Now, iodine is going to be the parent element. That means that's what we're starting with. And it's going to form the daughter product. So we can kind of do that. One of the interesting things is this nuclear decay happens over certain rates, and it goes by half-lives. And a half-life is where half the original sample is going to decay down to the daughter product. So if we look here, we start off with all parent sample here. After one half-life, we're at half parent here and half daughter there. We go through another half-life and we cut whatever we had in half, so now we have a quarter, and we'll have 3/4 daughter, and after 3 we'll have an eighth. And that helps us because we can look at that ratio from parent element to daughter product, and that's how we do radiometric dating. So taking a look at this chart from the lessons, you can see that we have our radioactive parent, and then we have our stable daughter product. And then we can get some ideas here of half-lives. So uranium-238 is going to decay down into lead-206, and it takes about 4.5 billion years for this to happen, and that's about the age of the Earth. So that means any of the uranium-238 that was around, we now have half as much. Half of it has decayed down into this lead-206. And you can see some of the other ones here as well. We have uranium-235, we have thorium-232, potassium-40, and these are all different radioactive isotopes that we use for some of this radiometric dating. Now, perhaps the most common one that you've heard of is using this carbon-14 dating here. And carbon-14 is kind of interesting. What we'll have is we have this nitrogen-14 that's out in the atmosphere, and we have cosmic radiation. So gamma radiation from the sun is going to cause neutron capture, and that's what's going to form this carbon-14. Now, carbon-14 is going to be taken in by animals through breathing, through eating, all of that kind of stuff. And then once it dies, we no longer have this, and we start seeing that carbon-14 break back down into nitrogen-14. So we can take organic material that had this carbon incorporated into it, and we can use that to find out how old or how long ago those things passed away. And carbon-14 is going to get us back to about 50,000 years or so. So it gives us a more recent way of measuring the ages of like remains and things of that nature. Now, radiometric dating can work when we're using like igneous materials and when we're using things of that nature, metamorphic materials, but it doesn't work so well when we're talking about sedimentary rocks. And the reason for that is sedimentary rocks are made up of sediment, and that sediment is going to have been eroded away. So we can have some igneous rocks that we can date radiometrically, but then they break away and then they form into this sedimentary rock, and we don't know when that sedimentary process happened. So what we can do is we can use a lot of times, we can use inclusions and intrusions of igneous materials, and that'll give us the ability to kind of roughly date these sedimentary rocks. So if we notice here we have a volcanic ash bed that was 160 million years, we know that these are going to be older than that, and everything above it is going to be younger than that. And if we have this intrusion here at 66 million, then we know this Wasatch on top is going to be younger than 66 million, but we know that these here are going to be older than that 66 million years. Okay, so that's the end of our video. As always, the lessons will go into a lot more detail. I just wanted to give you a quick introduction. Good luck on your quiz, and we'll see you in the next video. Okay, so in your lesson, you're going to see this picture show up a bunch, and this one kind of shows us what the geologic time scale is. What it was is it was a way of organizing what's happened in Earth's past into a way that we kind of can make sense. So it's taking the information and putting it into a way that we kind of understand it. We broke down geologic time scale first into its largest divisions are going to be the eons, and you can see that there are 4 of them, and we'll talk about them in a couple slides. We also have the eras, and there's going to be 3 major eras of the last eon that we'll talk about, and then we'll talk about periods a little bit more in the next coming videos. So when we look at the eons that have happened, there's 4 major eons that we talk about. The first was the Hadean eon, and that happened from about 4.6 to 4 billion years ago. And this is the formation of Earth was happening then. So the accepted age of the Earth is about 4.6 billion years ago. So that's when the Hadean started. And it's going to basically take us through the first 500 million years or so of Earth's history. It's followed by the Archean one, which is going to take us from 4 to about 2.5 billion years ago. And this is where we're seeing the formation of crust, the formation of the atmosphere, the formation of oceans, and things of that nature. That's followed by the Proterozoic era, and that's going to take us all the way from 2.5 billion years to about 500 million years ago. And Proterozoic means early life. So these areas here, what we're talking about is they're taking about 4 billion years of time. And our drawing's not to scale because we have a lot more information. We have more fossils, we can read the rock record, and that's going to tell us a lot more about our most recent era, which is the Phanerozoic era, and that means visible life. So we're going to start seeing multicellular things. We see a lot more formations, we have a lot more information. So when we look at our geologic time, we're seeing that we can break this one down, this Phanerozoic, down a lot more. So notice that this is not the scale by time, but it kind of breaks it down so we can see what was going on. Now within the Phanerozoic eon, about the last 500 million years, we break it down into 3 different eras, and we're going to study those in the upcoming videos. The first one was the Paleozoic, and that's ancient life, and that's where we see most modern groups of animals and organisms and plants evolve. So we're seeing most of the types of organisms. We're not seeing modern day ones, but at least we're seeing the types. That was followed by the Mesozoic era, and that's where we see a lot of forests and reptiles, and Mesozoic means middle life. And then the most recent era is going to be the Cenozoic era, and we're still in the Cenozoic era. And that one is where we see the rise of mammals, birds, and flowering plants. And as I mentioned, we'll be talking about these in a lot more detail in the upcoming videos. Okay, so as I was telling you, this isn't exactly to scale. Here we have about 4 billion years. Okay, and that's going to be the Precambrian time, and that's where we're talking about this Proterozoic, the Archean, and the Hadean eons. And that's going to be followed by the last 500 million years of this Phanerozoic one. And that was broken down into 3 different eras, the Paleozoic, the Mesozoic, and then the Cenozoic. And what we're going to do is we're going to go through and we're going to talk a little bit about the next periods of these eras in the next 3 videos. So we'll look at each of these 3 eras independently, and that's what we'll be spending in the next couple videos, looking to see what happened. And here I just wanted to show you another picture. It kind of shows you the same thing. We can see our time going along here. Notice it's not to scale, but on the other side, I thought that was kind of neat that it kind of showed you some representative things that were going on there. So you can kind of see how we have some primitive life here, single-celled organisms, and we can see how complexity and different types have evolved up over time. So that's it for this video. Good luck on your quiz and your lessons, and we'll see you in the next video.